Welcome to this video on Hess's law. Now, Hess's law in simple terms states that enthalpy change of a reaction is independent of the route taken through which the reaction happens. So, what do I mean by this? Well, let's draw an example. So, let's say on the left we have reactants and products on the right, and the enthalpy change is delta H. So, there are two routes for this reaction. Reactants are converted into intermediate A before they are converted into products, or they are converted into intermediate B and then they are converted into products. Whatever route you take, your enthalpy change will always be the same. Therefore, enthalpy change is not affected by which route you take to get from the reactants to the products. On to how to use Hess's cycle to calculate enthalpy change. So, what you need to realize, to answer these questions, you must pay close attention as to what information you are provided with in the question. So if you're provided in the question with enthalpy of formation data, then to calculate enthalpy change, you need to do the sum of the enthalpy of formation products subtracted by the sum of the enthalpy of formation reactants. What do I mean by this? Sum, so sigma, sum of enthalpy of formation of the products subtracted by the enthalpy of formation of reactants. So what does it exactly mean? Well, if you had a question saying calculate the enthalpy change of a reaction using the formation data, and the reaction is CaCO3 goes to CaO plus CO2. So how do you use formation data to calculate enthalpy change? So how do you do this? So let's run through the steps. So this is your enthalpy of formation data. And what you need to do is basically, first step, draw the Hess cycle. So that's our reaction taking place. Now, using enthalpy of formation data, so at the bottom of this reaction, we need to put the quantity of our elements in the reactants in standard states. Looking at the reactants, we can see that it is made up of 1 calcium, standard state is solid, 1 carbon, standard state solid, and 3 oxygens. Standard state of oxygen is O2, so we have to put 3 over 2. Now in enthalpy of formation, 1 mole of a substance is formed from its elements under standard states. So the arrows point towards the reactants and products. And last step is use products, sum of products minus sum of reactants, taking into account the stoichiometric ratio. So let's solve this then. So enthalpy of formation of calcium carbonate is minus 1207. Enthalpy of formation of calcium oxide is minus 635, and carbon dioxide minus 394. So enthalpy change is sum of products. So the products are minus 635 minus 394, the sum of the products, subtracted by the enthalpy of formation of the sum of the reactants. So sum of reactants is minus 1207, and we get an answer of positive 178 kilojoules per mole. Now, let's say we had entropy of combustion data instead of entropy of formation data. How would we solve it now? Well, we'd solve it using the same steps. So first step, draw Hess cycle. Well, at the bottom of the reaction, put the products of the combustion of the reactants. So our reactants in this equation are carbon and hydrogen. So our products of the combustion is going to be carbon dioxide and water. Now, in combustion, we point the arrows downwards. And we don't use sum of products, take away sum of reactants. We use the sum of the entropy of combustion of reactants minus sum of entropy of combustion of products. So putting in our values, so carbon has an entropy of combustion of 394, hydrogen minus 286, and methylbenzene 3909. So and the delta H can be calculated now using the sum of the reactants take with the sum of the products, taking into account the stoichiometric ratios. So what this means is we have 7 carbons, 4 hydrogens. So what this means now, the sum of the reactants will be 7 times the entropy of combustion of carbon, which is 394, plus 4 times the entropy of combustion of hydrogen, which is minus 286, subtracted by the sum of the products, which is minus 3909, and we get an answer for delta H of plus 7 kilojoules per mole. So to summarize, Hess's law. It states that enthalpy change of a reaction is independent of the route taken through which the reaction occurs. So how to use Hess's cycles to calculate enthalpy change? Well, if you are given enthalpy of formation data, then you do the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of reactants. And remember, at the bottom of enthalpy, using enthalpy of formation data, put the elements in their standard states and the quantity of which they are present within the reactants. So here we can see that there was 1 calcium, 1 carbon, and 3 oxygens. Now, entropy of combustion data, we have to use the sum of the entropy of combustion of the reactants minus the sum of the entropy of combustion of products. So draw the Hess cycle, put the products of the combustion at the bottom instead of the elements, point the arrows downwards, and use sum of reactants take away products, taking into account stoichiometric ratios. So whatever is in front of, say, carbon, hydrogen, you have to obviously multiply your entropy of combustion by that value to get your correct answer.